name's Quinn Armitage. I am from Service Heat Treating and a member of the MTI. I'd like to welcome you all to FNA 2024. Technical sessions today are presented by the MTI and MTI Educational Foundation. Before I introduce the speaker, I would like to cover a few housekeeping items. First, we'd appreciate it if everyone silenced their cell phones and put them away so we don't distract our presenter. FNA is officially videotaping all the sessions. They will be available after FNA 2024. So we ask that you keep your phones away, no pictures or video throughout the presentation. If we do see anyone taking pictures or video, we'll ask you to put your phone away. Please be respectful of that request and also of our speaker. Lastly, on the walls, you'll notice there are QR codes. You can scan these. It'll take you to the survey for the presentation. It actually brings up all the presentations, so just scroll down to the session that you're currently in. Answer a few questions. It helps to get feedback for the MTI and future presentations. Every survey that you do fill out, you're entered to win a $100 Amazon gift card. So now for our session. We have Mr. Roy Hardy. The presentation is going to be what is stoichiometric combustion and why is it important? Heat-treated parts are often processed through gas-fired furnaces. In those cases, a heat treater's business performance is dependent on the furnace's combustion system performance. This presentation explores the impact on a furnace's performance of maintaining stoichiometric combustion and maintaining stoichiometric combustion. Includes case studies to illustrate the variability of combustion systems. So let's give a warm welcome to Mr. Roy Hardy.
Thanks everyone for coming and being brave enough to come to a presentation that has the word stoichiometric in its title. Usually that clears out the room, so apparently you guys are a lot smarter than usual, or maybe the other way. But we are going to talk a little bit today about combustion and why it's important. And the truth is it's critical when it comes to your business performance. How well your furnace is running has a direct impact on whether you can make a profit or not. And in truth, in commercial heat treating, it's hard enough to make a profit even when the furnaces are running right. So I am Roy Hardy. I'm with a company called PSNERGY, and let's jump into this. So we're going to take a slide or two to talk a little bit about what is combustion. It is chemistry. There's a little bit of science involved. But some of that science is really important when you're taking a look at how well the furnace performs. So at a very basic level, combustion is a rapid combination of oxygen with the fuel. For our purposes today, we're going to be talking about natural gas. You need a source of ignition, and when you do that, it releases heat. The oxygen that you need comes from air in that burner, but it's important to remember that air is about 21% oxygen, about 78% nitrogen. And that's important when you start looking at, I'm using excess air. And there's reasons sometimes when you use excess air, but when you do that, you are providing more nitrogen, which has an impact on the efficiency of the burner. Again, we're going to talk about natural gas this time, but natural gas consists of carbon and hydrogen, the old CH4. Very simply put, and I like to keep things simple, so if you want to get very technical on this, you'll have to find someone else to talk about it. But combustion consists of carbon plus oxygen gives you carbon dioxide and heat, hydrogen and oxygen, water vapor, and heat. And it's the heat generated from these reactions that's used to heat up the steel or aluminum that's being processed in your furnaces. It is a combustion obtained by mixing and burning the exact proportions of fuel, again, natural gas and oxygen, so that nothing is left over. The idea, stoichiometric combustion, is just enough air and oxygen then to consume all of the natural gas that you have. If you have too much oxygen, excess air, that's called lean. The fire is oxidizing. The excess oxygen does not play a part in the process. So you have more air than you need, and the impact of that is now you have a lot more nitrogen than you need, and you're heating up nitrogen because that nitrogen absorbs heat, resulting in a lower flame temperature, decreasing efficiency, and increasing NOx. If you have too much fuel, again, natural gas, that's referred to as rich. So again, these are super technical terms that we use, rich and lean, but they do represent something. Fire is reducing. It's also called incomplete combustion, which results in smoking, sooting. Sometimes you even see it's almost like it's snowing carbon around your burners. So a little background on PSNERGY. We've been in the business of tuning furnaces for almost 15 years, so we know a little bit about burners. The technology that we have now supply people are the result of those years of experience. But we often walk into companies and say, how are your furnaces? They're running fine. They're tuned okay. When was the last time you tuned them? When did Pete retire? And so it's maybe been years, but they're still making flames. The flame's not too blue or too yellow, which we find people that are tuning by color. But if you look around the burners and there's evidence of a carbon snowstorm, that's a pretty strong indicator that you're running too rich, which is what we're talking about here. And the biggest problem with that is this idea of carbon monoxide. Sometimes we visit facilities where all the maintenance guys are wearing monitors that the bell rings after they've been around too much CO. That's an issue because too much CO at a bare minimum, you'll fall down and bump your head, or it could kill you. So carbon monoxide is a thing. So this is a little graph that just, again, this idea that the products that you process go through a furnace or multiple furnaces. The efficiency and therefore the safe transfer of energy to the load defines furnace performance. In the businesses you're in, your business performance then is directly tied to your furnace performance. As I said before, it's hard enough to make a profit when everything is running right. If your equipment is running inefficient, it becomes much harder. The other thing that's happened in the last few years, and we're seeing this, we do a fair amount of work with big steel and big aluminum, is this idea of scope. So in the food chain, if General Motors is out here, Caterpillar, John Deere, you're operating to where your scope 1, the CO2 that you're producing, if you're not doing it now, there'll be a day when you have to report that to your customers. So your scope 1 becomes part of their scope 3, which is they add up all their scopes, 1s and 3s, and then there'll be a day, and it's coming soon, where they'll be reporting that. And when that day happens, they'll be pushing you to reduce your scope 1, which will then reduce their scope. So this is an important item that you really need to be starting to think about if you're not already. Got to have a Sankey diagram. Can't be talking about furnaces and heat transfer and all that kind of stuff without a Sankey diagram. And so we've got one. The bottom line in what we're talking about, though, is out here. Heat to the load. Regardless of how efficient your burners are running, you're still going to lose some heat through the wall. You've still got flues. There's various places where you lose the heat. But what we're talking about is if I'm buying this much, I want to be sure that I get as big a percentage of that actually to the metal. And combustion is something you have a little bit of control over. And so that's what we're talking about. Better combustion, more heat to the load, more opportunity to make a profit. Got to have a few graphs. So stoichiometric combustion is 10 parts of air to 1 part gas. That's ideal. That's perfect combustion. But in truth, even if you could set your furnace up 10 to 1, and you can, now you don't have enough air to actually combust all the fuel. For all of the fuel to be burned, it needs to actually get close and rub against some oxygen so it can be consumed. I say here, find each other. So in an industrial setting, an industrial furnace, the truth is 10 to 1 is going to give you extremely rich, and you can see by the graph, lots and lots and lots of CO, and it's because it can't be consumed, you don't have enough air. So we're going to take a look at this graph and just talk about what each of these different lines represent. The blue line is ideal. And ideal is 11-ish to 1 air to fuel. It's about 2% excess oxygen if you're looking at excess oxygen. In a lot of your furnaces, I know, in a previous life I was a heat treater, I'll admit that in this room, is in radiant tubes. And so in radiant tubes, it's very easy then to measure excess oxygen in the exhaust leg of the tube. But you want to be around 2% is ideal to where now you've got enough air mixing with the fuel that you can get complete combustion. However, when you're running your furnace at 2%, it doesn't take much that it starts to leak into the 1.9, the 1.8, the 1.7, because there's a reasonable chance you're probably not tuning each burner every day. And so we say, again, from our years of being furnace tuning guys, that you want to be here when what we call safe, so when it does drift around, you never get into that danger zone. And and I've got a few slides in a minute looking at this particular case study. We've tuned enough furnaces to know that when a burner starts to go rich, it does not self-correct. It doesn't go to 1.6 and then turn around and walk back over to 2.5 or 3.7. Once they start to go rich, they just get richer, because again, the soot's building up, and so you start to have a real issue. And if you go lean, the issue of that is you really start to get some loss in heat output of the flame. So what we see here is, again, ideal in a perfect world is maximum heat output. As you get leaner, the heat really drops off. So it's safe. You're never going to form CO, but it becomes more and more inefficient. And so where you want to live with your furnaces is in here. But as you know, if you've ever been the guy that had to go actually out and tune the burners on your IQ furnace, your 24-tube pusher furnace, your 18-tube box annealing furnace, it's typically hot. It's tricky. And we know, again, from a lot of tuning of furnaces, it's just important to balance the zone as it is to tune the burners in the zone. So the right way to do it is if you've got 10 burners in a zone, burner number 1, burner number 2, all the way to 10, and then turn around and go 10 to 1, and then 1 to 10, and you do that enough times until finally they're all in balance as well as tuned. Well, that takes a hell of a lot of time. And again, this idea that if I start to go rich, I'm forming CO, it goes up pretty quick. In addition to being messy and dirty and inefficient, it's also dangerous. In the world of heat treating for gas firing, there's really 2 basic ways to do it: radiant tubes and direct or open fire. Some people call them direct, some people call them open. But in the end, you got a flame that's actually making the radiation to heat up the metal. Radiant tubes, you're trying to protect the metal from the products of combustion. We're heating up the surface of the radiant tube, which creates radiant heat, infrared radiant heat. Again, combustion is contained within the tube to protect the metal. Primary source of heat transfer is radiation. Open flame burners, you can actually look in and see the flame, which again makes them a hell of a lot easier to tune if you're tuning to color. We don't recommend you tune by color, by the way. And we've actually met people who tune by sound. They listen to the open flame, and they can tell by the sound of the flame whether it's in tune or not. You got to be really good to do that. The truth is you can't, but again, that's how some people do it. Combustion is open to the furnace, so metal is being processed is exposed to the product's combustion. We see a lot of these in tempering furnaces, low temps. We see a lot of them in reheat furnaces and steel. We spend a fair amount of time at Cliffs and Nucor, Steel Dynamics. And so in a reheat furnace, they'll have 4, 5, 6 dozen of those at 1.5 million BTUs per hour burners. So, but they don't really care about oxidation at that point because it's on steel plate and bars. Heat transfers by radiation is dependent on the luminosity. I've been practicing saying that for a week. I got it right. Luminosity, I think that's right, and the shape of the flame. So an out-of-tune inefficiency table, and this is generated by some equations that the Department of Energy provides. You could make one of these yourself, or we could provide one. But again, if you look at 5% excess oxygen, which in a lot of places we go is considered pretty good, and it's not bad, a little over 12 to 1 air to fuel. But if you look down here and look at your operating temperatures, what is the temperature, exhaust temperature? I mean, you start to look into some real inefficiencies, 6, 7, 8% in a burner that most people think's tuned pretty well. And we sometimes walk up to furnaces and check the excess oxygen. It might be out here in the 7 and 8s. And again, I got a case study we'll look at in a minute. And if you're at 14 or 1500 degrees, now you're getting into the 15 and 20% inefficiencies. And again, that cuts 2 ways. 1, you're buying gas you don't need. And 2, because you're burning more gas than you need, you're making more CO2 than you should or would if the burner was properly tuned. So when you start looking at these things on why is it important to maintain a proper combustion in a furnace, there's certainly a cost element of that, and depending on how much the gas is, you know, the president of our company, Carl's in the room, and I've told him that in years past, when gas is $12 an MCF, I'm a much better salesman than I am when it's $4 an MCF. So I'm banking on some more $12 MCFs. Maybe I'll make my bonus. But again, there's a huge impact here on just being just a little bit out of tune. And so that's the purpose of this. This idea again of CO2, very typical furnace, 28 tube pusher carburizing furnace, normal regular burners, 150,000 BTUs per hour. You do a little bit of math. The important part of here is 1 MCF of natural gas produces, I've seen numbers as high into the 122, 125 pounds. We'll stay conservative, 117 pounds of CO2 for every MCF. Do a little math. If the furnace is running exactly the way it's supposed to, you're still forming almost 500 pounds of CO2 per hour. If you're only 6% off, another 70 pounds. Roy, what's 70 pounds? We'll start doing a little math on a 24/7 operation in a pusher furnace, and if you're a big captive shop with 6 or 8 or 10 of these pushers sitting around, I mean, it adds up quick. 24/7 operation, over 50,000 pounds of CO2 times 5 furnaces. I mean, again, it starts adding up. And if instead of 6% excess oxygen, you're at 8% excess oxygen, and it's not linear, I mean, it actually starts, it's not really exponential, but it certainly speeds up quicker than just linear. So the more out of tune you are, the more CO2. And again, if that's not an issue for you yet, it will be soon. That says radiant tube box annealing furnace. I need a bigger screen with 44 U-tubes. So this is a furnace, no names please, it's a big box annealing furnace that we have tuned for years. You can see the initial data point here is October of 2019, which when I first started showing this slide seemed like it wasn't that long ago. Hell's bells, man, it's 6 years now already. October of 19, what you see here is the red dots represent the initial excess oxygen readings when we walked in on top of the furnace. The blue is where the furnace, each burner was excess oxygen when we left. So we walk in, we hook our gear up to tune, and you can see 4.3, 6.2, 7.9, 7.6. Several of them are running way too rich. So in addition to being inefficient, if you remember that yellow line, also forming CO2. When it was all tuned, we walked out, we gave them a 4% efficiency improvement. Everybody was happy. Again, when we started there, when was the last time you tuned this? When did Pete die? Oh yeah, okay, it's been a while. So, not to give too much information away, but this is an aerospace application, which means it has to pass a temperature uniformity survey. The only way to do that is if the burners are at least reasonably close to what they ought to be. So, everybody's happy, they passed their temperature uniformity survey. Why don't you guys come back in 6 months and tune it again? What do you think? How do you think that furnace looked 6 months later? You'd think, well, geez, how bad could it be in 6 months? All the burners are out of tune again. Damnedest thing. Helps us stay in business because we get to tune a little more often. I see a smile back there, you're right. But they're all out of tune again. Tune it, pass temperature uniformity survey, everybody's happy. See you in 6 months. What the hell? We've also looked at this. A burner that's rich this time may be lean the next time. Might be rich. The point is it's very hard, I would say difficult to impossible to actually predict what each burner is going to do. So there is some people who would tell you can do predictive and know which burner's doing what over time. We haven't seen that. We've just seen burners going out of tune. And in this case, they were all rich. So we tuned them, everybody's blue again, 7% efficiency improvement, back in 6 months. And so as I say, I would be willing to bet one of my kids, and you could pick which one you want, that it did not go that far out of tune the day after we tuned it. But I would also guarantee you that it didn't go that far out of tune the day before we came back to tune it again. So what that says to you is that they, and again, ones that go lean, go leaner, ones that go richer. But if you're running military, aerospace, applications where temperature uniformity is everything, at what point did it kind of go out? At what point did the door fall off? And I know the door was for bolts, but it makes more dramatic story. At what point would the door have fallen off the airplane or the wing or whatever it is? So for temperature uniformity surveys, it's critical to know what every burner is doing every day, so the work is always good, not, hell, we didn't pass the temperature uniformity survey after 3 months, 6 months. Quick, let's get it back to where it needs to be. Oh, look, now we passed the temperature uniformity survey. But when did it go bad? And I think there's another slide or two. The point is, it does that a lot. Every 6 months. A annealing furnace with 44 U-tubes maintained every 6 months was always out of tune. Now, because I'm the sales guy, I asked this customer, could we do the temperature uniformity survey before I tune it? No. Would it have passed? Yeah, maybe. Would it have failed? Yeah, maybe. Something to think about. But what if it was possible if you could keep every burner tuned to, again, 3%, 2%? The truth is if you actually could do it every day, you could start getting a little closer to 2% than the 3%, because as it drifts, you'll catch it before it gets you in trouble. The efficiency improvement would deliver more heat to the steel or aluminum, reduce emissions, reduce energy costs, and improve temperature uniformity, and it would be safer for your employees, and you wouldn't need as many maintenance guys running around trying to keep the furnaces maintained. This is where the sales pitch starts. It's now possible to know what every burner is doing every day. Booth 228, booth 228. There is an industrial Internet of Things combustion monitoring system available, probably on special today. You'd have to talk to Carl about that. Radiant tube and open fire. We can actually monitor every burner every day. So you can keep all the burners tuned at all times. Full furnace trends are visible in data. Readings are taken automatically. Single point tuning adjustments. I'll show you in a minute a slide that allows you to surgically address any issue the furnace combustion system has as it's happening. So it's not a, hey, zone 3 is not getting the temperature anymore, and zone 3's got 14 burners in it, and you don't even know where to begin to start looking. You can actually see what they're all doing. This is an example of a radiant tube dashboard that you can mount on a wall, look at on your computer, on your iPad, however you'd want to receive the information. You can tell when the furnace is going to high fire. You can see what the excess oxygen is on every tube. Also do it on open fire, direct fire, where you can actually see then what is the BTU burner rate, what is the fire rate of each burner, what is the air to fuel ratio. And again, you get to look at things like pressures and flows of every burner all the time. And so what you could receive is a daily report, red, yellow, green, that would tell you that I got a couple burners that are red. I better go do something with those now. So grab your Allen wrench or your screwdriver and your phone and tune the burner. If they're yellow, okay, I probably ought to start watching that one because it's starting to drift. As we discussed before, it's not going to fix itself. But that's one you can start looking at. And then the green ones mean that's fine. We have a customer that has this system on 3 continuous annealing furnaces, 48 burners per furnace. They used to always be out of tune. Their maintenance lead now, on Monday morning, gets a report, and he has every burner in green in about 20 minutes. So all of us are shorthanded on staff. None of us, and we know because we try to hire people to still do service, none of us can find anyone that actually knows what the hell an industrial furnace is, let alone how to maintain it. And they're hot and dangerous and dirty. And some of this tuning has to be done on top of the furnace. That doesn't work real well in July and August. So what we have discovered, we were on a reheat furnace recently in Texas. It was all screwed up. Somewhere I've got a picture of me standing there. I'm running at about 106 degrees. It was a thermal picture. The burner itself, which is about from here to that screen, was 600 and some degrees. And we asked him, we said, how do you tune this? We don't. And you can't really blame them. So what if you could just tell, I got 2 burners, get those burners fixed, get the hell off, and then work on all the other stuff that's on the maintenance list. So again, we got an app, everybody's got an app, we got an app. So the benefits from maintaining proper combustion, let's review. Cost savings with lower energy used, better temperature uniformity, and again, depending on what you're processing, that's essential. And even if what you're processing isn't essential, it would be nice if every carburized load actually had the same case depth on it from load to load. More heat to the load, reducing ramp-up time. We've got some case studies, booth 228. We've got case studies that show on big box annealing furnaces, we can reduce the heat-up time by hours, which again equates to actually an extra load or two a week. Improve safety, I just talked about that. Increase alloy life of furnace components. All the alloy in your furnaces really like it when it's not too rich, and so you actually start to carburize your alloy. Those of you that know, when you start to carburize your alloy, it gets kind of brittle. And I don't know, a lot of us are kind of rough on our tooling and our baskets and our fixturing. So as it becomes brittle and you bang it around when it's brittle, it breaks. Alloy's expensive. Decrease in emissions, decrease downtime for maintenance. Key point, I'm going to end on this one. I think this is my last slide. Yep, I get to say thank you in a minute. Remember that if no one's asking you for your scopes, they're going to. And Kevin goes, They're going to. And that's me. Thank you very much. At this point, I think I got a few minutes left to take some questions. Okay, sir.
You mentioned, oxygen seems pretty easy and obvious for radiant tubes to monitor each individual burner. For a direct fired furnace, what do you do for monitoring each individual burner?
So there we're actually looking at the ratios of air to gas. So we're monitoring how much gas and how much air.
You're looking at valve position, or you're looking at orifice meters?
Yeah, so we're, go ahead, Carl. Yeah. So when we're reporting what is the fire rate, we're calculating that from the actual flow and pressures of gas and air, and then also reporting that as well. So what is the real flow? And often there's many furnaces that are set up that can give you kind of a mass flow kind of deal on the zone. That's cool, but I still don't know what's going on at the burners. And so your zone can be in tune, and you go out and check all the burners, and they're all out of tune. But the rich ones and the lean ones all kind of counteract, and it ends up that the zone is balanced and in tune, but it's really not. What's important is what's happening at each burner. Any other questions?
I've heard different opinions on what you can learn from measuring the oxygen on an open-air box furnace like that, and I wondered what your opinion is about measuring the oxygen in an open-fire furnace.
So we see this at some companies that have a Radcon Ebner kind of bell furnace, and so they are taking the oxygen at the stack, if you will, again, a combination of all the burners. So that tells you what the furnace is producing, if you will, for CO2. So that's certainly information. And if it's really wacky, then you know you got a problem. But again, I can have rich burners and lean burners inside that bell that can give me a number that's not too bad at the stack, but it's still not telling me what's going on at each burner. So at that point, you can say I'm okay with CO2 in total, but I might still be super inefficient because I'm not looking at the burners. So I think that's what you can see. Sure.
Scott, I think that's a great question. The key for us, at least with PSNERGY, is how we provide data that's actionable, right? So measuring at the stack would be interesting. You might know that you have a problem, but what do I do with it? I still have to figure out which of those burners is causing me that problem or multiple. So by focusing in where the action happens at each burner, that gives the user actionable data to go do something. Okay.
Thanks, Carl. Any other questions?
All right, if we could give,
Oh, wait, I had one.
never mind.
You mentioned, a burner can go rich, go lean.
Yep,
One day versus the next month.
right.
And then you did mention soot as one possible,
A vindicator, yeah.
let's say situation that could cause that. What are some other things? Do you have any explanation why?
Yeah.
What else?
Well, and so that's a great question.
The valves aren't necessarily
That's right.
changing.
The valves aren't moving.
And your orifice plate is not necessarily changing.
Might start to plug or wear over time, but yes. And so let's think about where your air comes from. The air for these furnaces are all coming from the air inside the building, and you got a blower that's sucking air and blowing it into, and there's also filters. So as your filter gets dirty, it's not the same air as it was when you started. On a very humid day, it's different than in the winter when the air is very dry. As we know, natural gas is not always the same. Sometimes they spike it with other stuff. And so there's a few variables, not a million, but there's a few. But once some of those variables come into play, again, a burner that's beginning to soot is not going to self-clean itself. It's just going to continue to just get richer. So there's a handful of variables that cause that: quality of the gas, quality of the air. Because again, you've only got a couple inputs, but it's not always the same.
Right, can I just add one more thing?
Sure.
Sorry for that, but, again, another super question. That's why, at least in the PSNERGY system, you have two data sets, right? You have a point in time, and you have overtime, right? So, as you're looking for variations at a point in time, that's different than overtime. So if I keep changing, zone 2, burner 7 constantly, and I'm looking at that over time, now I'm going to start to hone in on that, saying, maybe I've got a burner problem, maybe I got a valve problem, maybe there's something else going on with that specific component set for that burner. So that's why point data is important, but over time data is also important. That's where the graphs come in. You can when you see, there's another presentation that we have where you can see so many different things when you're looking at that historical graph, where you can see plugged air filters, you can see bad regulators, you can see, the furnace calls for low fire, everybody responds except for burner 7, right? So that's the combination of those two really gets you to answer some of those questions that you're asking.
And that's a good point, something that I didn't explain, is that as we collect data, as the system collects data over time, in addition to spotting specific problems, you can see trends. The other thing that you can see is that, not that anyone in here has what we call combustion cowboys, but typically we have customers who have somebody on third shift who knows how to run the furnace better than anybody else. And so they're one of the guys that's in there adjusting burners because, that flame doesn't look like it's supposed to. Yeah. So again, just an advantage of this trending where you could go back because all the data would be yours and it's yours to look at. Yeah, something happens on third shift every week.
The valves do change.
So yeah, correct. So you are exactly right. With a little assistance, valves do change. And again, you can spot that. And again, I'm sure no one in this audience has that. But some companies do have what we call combustion cowboys who really, they know best. And so you've just spent thousands and thousands of dollars having that furnace tuned, and in 2 days it's just running like it was before. What the hell? Yeah, you probably got somebody with a screwdriver helping you when nobody's looking. Yeah.
Well, I don't know, I guess this is more kind of an opinion. I know, where when we do heat treat, it is common practice for the operator to vary the air pressure in order to redistribute the heat. To try to push it further into the furnace or further out, or try to get it under the part.
Is this open fire?
Yes.
Okay.
I guess kind of what would you say the consequences of this is, or is this more than convenient? I mean,
Well, our VP,
how do
yeah,
you view this
right.
taking place? Or
So the heat applied to the metal on open fire is very dependent on the shape of the flame and the lumicity of the flame. So there is a little bit of adjusting. Oh, I'll get the flame where I want it, or I need it a little bit longer, or whatever. But our VP of service would tell you there's actually a window that you get yourself in a lot of trouble when you're adjusting ratios by sight, sound, or whatever, that you can actually get into an explosive situation on one end or the other. So the danger, and there is a danger, if you're just out there doing this, you could get yourself into a place where all of a sudden the furnace, even just at that burner, goes boom, which would be rough on your refractory. And if a few of them went boom, it might be rough on the people standing around the furnace. So you can make adjustments when you have the data. Carl always says, if I have the data, now I can actually start to, well, what if I ran 12.5 to 1, because that's going to, okay, I'm going to lose some efficiencies, but I'm actually getting leaner, especially in open flame, and now I'm not forming an oxide on the part. So, I mean, there's things that you can do. But when you're just kind of blindly doing things, I mean, you can actually get yourself in a lot of trouble. And I know that people do that. We highly recommend they do not. But again, some of these, you have people who know better than you, or know better than experts, because I've been running this furnace since 1982. I know how the hell this thing runs. I was here when they put it in. Okay.
And they probably do have pretty good knowledge, right? But without the tool, without the visibility,
Yeah.
it's really, it can only be so. Once you have the data to see it, then you've given your staff the tool to make those good decisions, not put yourself in a dangerous situation. You know, my answer to your question is, I don't know, and neither do you, right? Because you don't have the data.
Yeah.
But if you have the data, it becomes easy.
Well, yeah, and I mean, you know, obviously, the air pressure is, you know, can be done manually, but I mean, there's still adaptive situations on the gas.
Yep.
Just one quick question.
Sure.
What is recommended if you, for the tuning versus the monitoring? Like, let's say you don't have the capital expenditures to do the monitoring, but you want to do tuning, just hope it's not every 6 months. What is the guy's recommendation?
So industry standard is you really should tune it every 6 months.
Okay.
If you're running aerospace quality, temperature uniformity surveys, some of them require tuning every 3 months, every month, depending on the product that you're processing. But things are expensive, but the question you have to ask is, what's the value? I'm in sales. It's about value, not the cost. And every situation is different, every furnace is different, and depending on what you're running in it is very important as well. This stuff's not cheap. If it was, Carl couldn't afford to hire me. But I mean, again, I think you shouldn't be afraid of at least exploring things that might get you where you want to be, and not be afraid of, oh, that's going to cost too much money. I mean, that's when you get out the pencil and figure out the paybacks and twist the sales guy's arm and that kind of stuff. Was there another question in the back? Thank you very much.